Let's have a look at linear regression in Gluon. So the first thing we need to do is we need to import MXNet, and we need to pick some inputs. So in this case, 2 dimensions, 1000 observations, and well, we need to pick some parameters for our linear function. So in this case, we are going to pick parameters 2 and 3.5, and then a bias of 4.2. So our features are going to be just drawn from a normal distribution. So we're going to draw from a 2-dimensional normal distribution 1000 observations in 2 dimensions. And then I perform linear regression, so features dot true W plus true B. In addition to that, I'm going to corrupt it with some noise, actually a very small amount of noise, just of scale 0.01. And that's my data. Okay. Next thing is I need to get my data. So I'm going to import my data operators from MXNet Gluon, import data as gdata. I'm going to pick a mini batch size of 10. And now my data set is just a generic array data set, so there are already some hooks for that. So it consists of features and labels. And my data loader will now do the following thing. It will actually generate random mini batches. So that's why I said, batch size of 10, shuffle equals true. So every time I go over the data set, it'll create a different shuffle. So if I want to see how that works, well, it's very easy. I just go and iterate over the data, and after the first batch I stop. So the pieces here, these are my covariates, so these are the x's, and these ones are my labels, these are the y's. And you can see the first thing is a 10 by 2 array, the second is a 10-dimensional vector, exactly as I would expect. Okay, so now that we have that, we need to introduce the model. So that's very easy. I just import my neural networks model. This is a sequential network. So in this case, there are no parallel network constructs. So that's going to be the default for now. And I'm going to add exactly a single dense layer, which is going to take all the inputs. It's going to produce one output, hence dense of 1. Okay, the next thing I need to do is I need to initialize the model parameters. And for lack of any other better knowledge, I'm just going to initialize all the model parameters. So this is in this case going to be W and B, all the entries, with normal noise with mean 0 and variance 0.01. Okay. I could have picked something else, but this is a very simple initialization. Okay, so next thing I need a loss function, and that's just the L2 loss. It's the least mean squares loss, also L2 norm loss. And we need an optimization algorithm. In this case, we're going to pick the same as before, namely stochastic gradient descent. And, well, for lack of better knowledge, we pick a learning rate of 0.03. We could have picked a larger or smaller learning rate, depending on, what's needed. But okay, let's just pick this. It's actually fairly resilient. Okay. And then I'm going to do the following thing. I'm going to iterate over the data 3 times. And yeah, okay, that works very quickly. So for epoch in the range of epochs, you basically go and iterate over the data. Now, so this gives me a mini batch each. And now I need to turn on autograd. So I'm going to compute the loss of net of x and y. I then compute the gradient. And now I'm going to take an update with a trainer with size, batch size. And that's it. And so in the end, I'm going to compute the loss, namely loss of all the network applied to all the data and all the labels, and I print it out. And that's it. This is how easily you can run optimization. Now the reason why trainer.step actually knew what to do is because we told it before what the parameters are. So if you look at the initialization of Gluon trainer, we give it already the parameters that it needs to optimize over. Because otherwise it seems like magic. How on earth would, this optimizer know what to do? Okay? So last but not least, let's have a look at what we get as an output. Let's see. And yes, what we actually find is if we compare the true W and the W that we estimate, we get it right with an error that's less than 0.01 in all the 3 cases. And that's good news. So in other words, this very simple stochastic gradient descent algorithm was able to estimate the parameters probably about as well as we could have hoped for. And yeah, it's a few lines of Gluon to make your life easy.